Hello everyone, welcome back to the NPTEL course on materials informatics. In this lecture we will continue our discussion on statistical mechanics, and just as a recap of what we did in the last lecture, we defined two different ensembles: microcanonical ensemble for modeling isolated systems and canonical ensemble for modeling systems under thermal equilibrium. We also took a deeper dive on entropy as a property of the macrostate, and its interpretation of how accessible the microstates are in a given system, right. So in this lecture we look at some more practical examples or practical systems that can be actually modeled with the ensembles that we have defined. So let us take a simple system which is often called a two state system here. So the definition of the system is like this, right. So we have n distinguishable particles. So think of these distinguishable particles as labeled atoms, right. So let us say you take an ideal gas, you actually manage to label all the atoms in the ideal gas, and then you examine the state of those state of the atoms, right. So so this is basically n distinguishable particles, and let us say each particle can have two possible energy states. So it can either have a ground state energy, which we are going to represent as 0, because in canonical ensemble the probability distribution is independent of the actual value of the ground state energy. So we are arbitrarily defining the ground state energy to be 0, and then some higher energy state which is referred to as epsilon. So epsilon is a positive number, it is greater than 0 here, right. So if you now take the partition function of any given n among these n distinguishable particles, if we take a partition function for any single particle, so let us say we now set n equals 1, right, then that partition function will be q equals 1 plus e to the power negative beta epsilon, right. So this is basically e to the power negative beta times 0, right. So that is one of the states, and then plus e to the power negative beta epsilon, that is the second state that particle can exist in, right. Now if the n particles are all independent, right, so if the particles are actually not interacting with one another, then we can define the partition function for the n particle system simply as the single particle partition function q, small q, to the power n, right. This has analogies to how you actually sum energies, right. So if you have energies of individual particles, the energy of the total system is basically a summation of the individual energies. In the case of partition function, it turns out to be the product, right. So the partition function of the overall system is basically the product of the individual partition functions. So you have n particles, so this is basically q power n. So this now becomes a very simple functional form, right. So your overall partition function for distinguishable independent particle systems in two energy states, right, is basically 1 plus e to the power negative beta epsilon the whole power n, right. Now let us consider a canonical ensemble of these n distinguishable particles with two possible energy states, right, n distinguishable independent particles with two possible energy states. So your number of particles is fixed, your n is fixed here, and so is the volume of your system and the temperature of your system, right. So if all these are fixed, you already know your partition function, right. So you can straight away determine your governing thermodynamic potential, which is your Helmholtz energy, right. So your F is nothing but negative kBT times ln q, this we saw in our previous lecture, right. So substitute q from here, you are basically going to get negative n times kBT times ln of 1 plus e to the power negative beta epsilon here, right. You can also now calculate entropy. So entropy is nothing but the thermal derivative of your your Helmholtz energy. So if you actually take the temperature derivative, you are going to get n times kb ln of your partition function, which is 1 plus e to the power negative beta epsilon. So this is the partition function for a single particle here, and then you will have e bar by t, that is your second term, which is what is represented here. So your average internal energy is basically your n epsilon by 1 plus e power beta epsilon, right, and beta is nothing but kBt, 1 over kBt, right. So this is basically your entropy. So this is something that you can mathematically define. So you just need to use the fact that your entropy is nothing but negative df dt. So just apply this fact in this equation and you should be able to get the following relation. Yeah. And this function is actually quite a nice function. So I leave it as a couple of take home exercises. So it's a very interesting function, try to see what the values of your entropy are as your temperature goes to 0 as well as your temperature goes towards infinity. You will have to use some mathematical techniques or limits basically to evaluate these values, but you will see that entropy will always take well defined values, right. So in other words, your values of your entropy and by extension your Helmholtz energy are bound, they are actually well defined at both 0 Kelvin, 0 temperature, and also at infinite temperature, right. So this is a very nice interesting mathematical function. You can also try to visualize this function to see how entropy will actually vary as a function of temperature. So I will leave that as a take home exercise. Okay, let us now further our discussion on this simple two state system. So our average energy is nothing but our n times our epsilon divided by 1 plus e power beta epsilon. This actually comes from our definition of our entropy itself. So we sort of wrote our entropy as kb ln q plus average energy by T. This is for the canonical ensemble, and from the previous slide we sort of got this as nkb ln of 1 plus e to the power negative beta epsilon. So that corresponds to the first term here, right, and the second term was basically n epsilon by T times 1 plus e to the power beta epsilon, and that basically corresponds to the second term here, right. So from that expression we can straight away get our average internal energy of our two state system, and that is basically this expression here, right. And if we think about what is the occupancy of the excited state in our system, so if there are let us say n particles in a system, if a fraction of those n particles are occupying in the excited state, right, then the energy of that excited state will basically be your average internal energy divided by the energy of the individual excited state itself, right, because the ground state has 0 energy. So if you have let us say if you have 0 occupancy of your particles in your excited state, then your average internal energy will actually be 0. Right, because all of your particles are in the ground state, so there is no energy in the excited state, so average internal energy will be 0 by definition. So we can also actually define the occupancy of the excited state as the average internal energy divided by the energy of the excited state itself, right, because this energy is epsilon is constant for each particle, and this occupancy is basically we get it as n by 1 plus e power beta epsilon, right. And this quantity is actually very useful. We will see how useful this quantity is in the next couple of slides. So this is these are some of the outcomes of our two state system, right. Now we can also model this two state system with a microcanonical ensemble as well. So far we have done it using a canonical ensemble, right, but we can also do it via using a microcanonical ensemble. The way we are going to do it is we are going to say that m out of n particles are in the excited state, right. So there are n independent particles. We are going to say that m out of this n is going to be in the excited state. So the energy of the ensemble is basically m times epsilon, right. So the number of particles in the excited state times the energy of the excited state, because ground state has 0 energy. So this is the energy of the ensemble itself, and now we are simply going to evaluate the degeneracy of this ensemble. So how many different combinations can I have where I put m out of n particles in the excited state, right. So I have basically a combinatorial problem here. So this is basically n choose m, right, that is my degeneracy of my system. So this is basically n factorial by m factorial times n minus m factorial, right, and I can, once I know my degeneracy, I can evaluate the entropy in my microcanonical ensemble. So this is nothing but kb times ln of my omega, and I could in fact relate temperature from my microcanonical ensemble as well. So I can define what temperature my system should exhibit in this microcanonical ensemble, because I fix my energy, so I can always define my temperature that my system should exhibit, and that definition also comes from macroscopic thermodynamics. So we actually take dsDE, that is nothing but 1 over T. I mean this you can straightforwardly see from the definition of our internal energy. So our internal energy was dE equals TdS minus PdV plus mu dN, right. So if you take dE ds, right, at constant volume number of moles, this is nothing but temperature, and if you take the reciprocal of it, you basically get ds dE at constant volume and number of moles. right. So, you can sort of straightforwardly derive this from macroscopic thermodynamics. Okay. Let us now try to see how this entropy function looks like. So, we said that entropy is kb ln omega if we are treating the two state system with microcanonical ensemble, and we also define omega, this is just the combinatorics, right. So, how many combinations of m particles in the excited state we have, right, given the total number of particles that we have is n. So we basically let us say if you want to calculate temperature, right, we have to take the derivative of entropy with respect to the sort of ensemble energy of the system or total internal energy of the system, and we know that E equals m times epsilon, right, and epsilon is a constant quantity, m can vary, the number of particles in the excited state can actually vary, right, because that is our choice. So, we can put in how many other particles we want, right, those will basically create variations with our microcanonical ensemble. So this can actually vary. So, we basically state that this is 1 over epsilon dou s by dou m, right, and this should be related to our temperature, right. So, if you now assume that both our n and m are large numbers, we can basically use Stirling's approximation, and if you actually do the math, we will basically get our m as n by 1 plus e power beta times epsilon. So, the temperature term actually goes within this beta term here, right, and this is nothing but the same as our occupancy in our canonical ensemble, right, and if you actually get energy, right, so the total ensemble energy of the system, this is nothing but m times epsilon. So, we know n from here, and if we just multiply this with epsilon, this is also the same as what we derived in our canonical ensemble, right. So, we see that both the canonical and the grand canonical ensemble yielded us the same quantities. So, both occupancy and average energy here the same quantities as the other ensemble. So, whether we model with canonical or whether we model with microcanonical, we got the same answers, right, and this is actually true in statistical mechanics in general. So, all ensembles will yield the same thermodynamic properties at large system sizes, right. So, this principle is referred to as the equivalence of ensembles. So, under the large system limits, all ensembles will give you the same thermodynamic properties. So, you can choose to model a given system in any ensemble that you want to, right, whichever makes the mathematics a little simpler, right, and as long as the system size is large enough, the thermodynamic properties that you calculate, the averaged quantities that you calculate should be the same, right. So, if you were to calculate entropy in a canonical ensemble, it should be the same as so if you calculate entropy as a function of energy in your canonical ensemble, you should get the equivalent energy as a function of entropy in your microcanonical ensemble, right. This you can also extend in the terms of temperature calculations, right. So, if you calculate energy as a function of temperature in canonical, this should be the same as temperature as a function of energy in your microcanonical ensemble as well, right. So, the properties that you can calculate are actually equivalent as long as the system sizes are large enough in your ensembles, right. So far we have looked at canonical and microcanonical ensembles. We can also generalize and look at other possible ensembles. So, the one extension that we can think of is grand canonical ensemble, where we take the grand canonical potential as the governing thermodynamic potential. So, this is E minus Ts minus mu n. So, this is very relevant for open systems. So, you see the d phi equals negative SDT negative PdV minus ND mu, right. So, your phi becomes minimum for a system at equilibrium under isothermal, isochoric and open conditions, right. So, if you actually write down the grand canonical partition function, you can actually write this as a simple product of your canonical partition function for a given number of particles in your system times e to the power beta times mu n, right, and then sum this over the different number of particles that you can actually have in your system. So, sum this over all possible states where the number of particles are actually changing, right. So, this way of writing is basically a generalization of writing it in this form. So, instead of just e to the power negative beta times your e, you have e minus mu n coming in here, right. And once you know this grand canonical partition function, you can write your thermodynamic potential as your grand canonical potential as nothing but negative kBt ln of your grand canonical partition function, right. So, this idea is actually generally true for all ensembles. So, your governing potential will always be negative kBt times ln of your corresponding partition function, right. And if you were to derive entropy from this, you will see that it is nothing but kB times ln of your q your partition function here plus your E by T, this is the same as your canonical ensemble, and you get one additional term which is n mu by T here, right, where n mu by T sort of comes from this term here. And the way you sort of get this is by accounting for the fact that your d phi is basically negative SDT minus PdV minus ND mu here. So you can write your entropy as basically negative d phi dt at constant volume and chemical potential, right. So if you were to actually do that, you will get this relation here, right. And just like your canonical and microcanonical are equivalent at large system sizes, large ensemble sizes, your canonical and grand canonical ensembles are also equivalent at large sizes. And one way to sort of check it is if you calculate your chemical potential as a function of number of particles, right, in your canonical ensemble. So number of particles is what you control, chemical potential is what you calculate in canonical. This will be the same as number of particles for a given chemical potential in grand canonical. So chemical potential is what you control and number of particles is what you calculate, right. So mu of n, this function will be the same as n of mu in your grand canonical ensemble as long as the system sizes are large. Okay. So we can actually generalize this behavior of ensembles into a generalized box ensemble. So where we define the partition function as e to the power this box of I, right, divided by z. So z is our so we define probabilities as e to the power box of I divided by z. So where this box basically whatever values go on this box and whatever is your partition function depends on your boundary conditions of your ensemble. So for this corresponding box ensemble we can also define a corresponding thermodynamic potential which is lambda. Lambda would be some kind of a Legendre transform of our internal energy here. So this lambda we can define as negative ln z, negative ln of our partition function divided by our beta, right. So this relationship is universal. So our governing potential lambda is a Legendre transform of E. So let us say our dE can be written as TdS plus xdy, right, and our Legendre transform lambda is basically a Legendre transform with respect to entropy and our y here, right. So we basically get this as E minus Ts minus xy. So our d lambda would be negative SDT minus y dx, right. So our box, so whatever should go within this box should basically be negative beta times EI minus xyi, right. So xy is what is given here. So you should basically vary it as the energy of that microstate and the corresponding displacement of that microstate for a given field variable, right. So this is what you should be put into the box here, and z would be basically summation of your e to the power box of I. So you can see that for canonical ensemble so for canonical ensemble your box is nothing but e to the power negative beta ei, but for grand canonical, right, your box is basically e to the power negative beta ei minus mu ni. So n is the displacement variable and that is what is varying for individual microstates, and mu is your control variable, right, in your grand canonical ensemble. Displacement, right. And your partition function is basically summation of this e to the power box items here. And for grand canonical ensemble the sort of governing potential is phi, right, and phi is nothing but E minus Ts minus mu n, right. Whereas for canonical ensemble your governing potential is just E minus Ts, which is your Helmholtz energy, right. So you can sort of write this. So if you want to consider a system that is under isothermal isobaric conditions, right, such as Gibbs energy, you can define the corresponding partition function, the corresponding thermodynamic potential which will be G here, all that in a fairly similar fashion here. So you can create an ensemble of any given box, any given boundary conditions and define the corresponding thermodynamic properties using this mathematical framework. Okay. The next idea that we can sort of think about in statistical mechanics is the idea of fluctuations. So all ensembles have certain quantities, basically the boundary conditions that are fixed, while other quantities can actually fluctuate. So for example, in the canonical ensemble your temperature is fixed, but your energies can actually fluctuate. So energies of your individual microstates, they are not fixed, so they can basically fluctuate to different values. The variance of such fluctuations are actually related to measurable properties, right. So in the case of so how do we define variance, right. So we can define variance of a given quantity as the average of the square of that quantity minus square of the average of that quantity. So it's E square bar minus E bar square, right. If you actually do the math, right, if you actually evaluate what these quantities are for a simple canonical ensemble, for example, you will get the sigma E square to be kBT square times Cv, right. So in other words, your specific heat at constant volume is actually related to the variance of your energy fluctuations, right. So in other words, specific heat is related to energy fluctuations in a system. The larger the energy fluctuations in your system, the larger the specific heat is, right. Similarly, if you do the same exercise for a grand canonical ensemble and calculate the variance of the number of particles, right, variance in the number of particles, you will see that this is actually related to your isothermal compressibility, right. So how compressible or not your system is actually related to your fluctuations in the number of particles in your system. So the more the number of particles can actually fluctuate in a system, the more compressible your system generally is, right. So in general your systems which have significant fluctuations, right, will be systems that are of small sizes. So where your number of particles is small or the number of energy levels are small. So in those cases you can have significant fluctuations, and you can have significant fluctuations whenever your system is approaching second order phase transitions. So your specific heat, your Cv here and your isothermal compressibilities will actually diverge, will exhibit a logarithmic spike whenever you are approaching second order phase transitions in your system. And this is actually how we identify second order phase transitions, right. So if you are simulating a system and if you are interested in identifying phase transitions using statistical mechanics, and if that phase transition is of second order, then the corresponding to those phase transitions you will see a spike in your specific heat or your compressibility. So if you keep tracking your specific heat, your energies will have very large fluctuations as they approach your second order phase transition. You can sort of think about why these fluctuations are large in terms of your convexity of your energy surface. So as you approach your second order phase transitions, your energy surface becomes fairly flat. So whatever small fluctuations you have in your energy surface, there is nothing to restore it to back into an equilibrium state, and the fluctuations keep expanding. So they expand, and then there is a sort of a wave-like transition that happens as the system approaches a second order phase transition. So fluctuations are very important in identifying second order phase transitions in systems. Okay. The other important idea to consider is the aspect of distinguishable versus indistinguishable particles, right. So in the previous scenario where we calculated for a two state system, right, we considered the scenario of a two state system with n particles which are distinguishable in nature, right. And usually in classical mechanics we deal with distinguishable particles. We can actually label the particles, so we can track the particles as they evolve, right, in a given box or in a given field. But when we are dealing with atoms, electrons and so on, so when we are dealing with microscopic particles, we often come across situations where particles are not distinguishable in nature. So to understand how this sort of varies, right. So let us say you have a two state system with two particles, and let us say both particles are actually distinguishable, right. Then you can have four possible arrangements, right. So either both particles can occupy the ground state, so zero energy state, either both particles can occupy the excited state, which is represented by 1 here, or either of them can occupy the excited state or not, right. And all of these four configurations are distinct. We can actually identify all these four configurations, and this is basically related to how we compute the partition function as well, right. So if you compute the individual partition function, you will just see that for n particles, n distinguishable particles, the overall partition function is just the individual partition function power n. So we just need to multiply the partition function of individual particles, right. So here for each particle your partition function is 1 plus e to the power beta epsilon, so you just do 1 plus e to the power beta epsilon the whole square, right. So that is the case of a classical particle. that is how classical particles generally behave in classical mechanics, and this is still useful if you think about how configurations in a spin lattice. So in a given solid structure you can actually label the atoms according to how they sit in a given cell, sit in a given box or a given lattice. So how configurations actually vary in a given lattice, this is this kind of a problem behaves in a classical manner. So where you can actually identify the different configurations. Similarly, how do gases adsorb on surface sites, because you can label the surface sites, and this has relevance for catalytic applications, right. So these kinds of practical problems you can actually deal with systems that behave in a classical manner. So where you identify the partition function associated with one lattice point or one gas adsorption site, and then you can generalize that to partition function across the entire system, right. And even if the case that particles are not distinguishable, so let us say you now have a ideal gas, right. So where you have atoms moving around in a box, even if particles are not distinguishable, you just need a small modification to this partition function in the large size limit. So if the number of particles are large, you just modify your partition function as q power n divided by n factorial. So the n factorial basically ensures that we are not double counting the indistinguishable particles, right, or we are not double counting the microstates that are possible. And whether we deal with classical particles in this manner or this manner, the resultant kind of statistics that we get is what is referred to as Maxwell-Boltzmann statistics, right. So Maxwell-Boltzmann statistics basically tells us what is the sort of let us say average occupancy of a given excited state is, right, in a two state system if the particles were to behave classically, right. So Maxwell-Boltzmann statistics is quite useful, and we can model many gases, we can model, as I said, spin lattices and even adsorption properties with Maxwell-Boltzmann statistics, and this is how classical particles generally behave. But when we go into quantum mechanics, then the behavior can be completely different. Generally quantum mechanics are not distinguishable, quantum particles are not distinguishable, so we cannot distinguish between different electrons, or we cannot distinguish between the different bosons, we cannot label them very easily, and they may have different occupation rules as well, right. So bosons, for example, are integer spin particles, and here bosons can multiple bosons can occupy the same energy state. So you can have situations of both bosons being in the ground state, both bosons being in the excited state, and one being in the excited state while the other is in the ground state, right. So 0 1 and 1 0 are the same here, right, because bosons are not distinguishable, so both those states are the same states for us. So for bosons, there are the way they or the microstates that are possible for them is basically determined by this Bose-Einstein statistics. Electrons, which are fermions, these are half integer spin particles, and here fermions have the occupancy rule that two identical fermions cannot occupy the same state or same energy level. So if you have electrons of two identical spins, they have to occupy two different energy states, right. So that is why you cannot have 0 0 1 1 kind of occupancies here, you can only have 0 1 occupancy here, and 0 1 is the same as 1 0 because electrons are not distinguishable, right. So you see that number of possible microstates are different, right, if you have indistinguishable particles. So if you have distinguishable particles, you have 4 different occupancies that are possible. If you have indistinguishable particles, you can have either 3 or 1 occupancy, right, depending on occupancy rules. And fermions obey these Fermi-Dirac statistics, right, as they sort of in terms of the number of microstates that are accessible to them, right. So whenever we are dealing with indistinguishable particles, we need to find a way to account for these kinds of occupancy rules, right, while computing the partition function. So if you think about how you are actually summing up the total energy of your system, right. So if you or energy of a given microstate of a system, this is actually not a trivial scenario, because you need to consider the energy of all possible states of your system and the number of particles that can actually occupy the different states of your system. So this sum is is sort of complicated, but it is possible to use mathematical tricks to do this, and the way we typically do it is we actually sum over the particles that can occupy an energy state instead of summing over the states themselves. So we sum over the different possible distributions basically under the constraint that the number of particles is a constant, right. And if we use this, we can actually model or we can do the summations more easily if we model are fermions and bosons to basically occupy a grand canonical ensemble. So where we introduce a chemical potential term and we sort of say that our bosons or fermions are in equilibrium with an external chemical potential, right. So using this grand canonical ensemble makes the summation easier, and if we do this we basically get an sort of an average occupancy term. So what is the average number of particles at a given chemical potential or at a given energy state, right, for our system. So if we skip the math we can actually get these kinds of distribution functions with Fermi-Dirac statistics which are suitable for fermions, for Bose-Einstein statistics which are suitable for bosons, and for Maxwell-Boltzmann statistics which are more for classical particles, right. And all of these distribution functions sort of converge to the same value or same distribution under very large energy levels. So the energy levels are very large in number, then they sort of converge to the same value, and as the temperature sort of approaches approaches 0, right. So if you go towards zero temperature, you see that the Fermi-Dirac statistics goes through some kind of a step function. So for energies below the Fermi level electrons occupy, and energies above the Fermi level they are not occupied. In the case of Bose-Einstein statistics you will see a divergence in occupancy. So energies below Fermi level sort of are infinitely occupied, energies above Fermi level are not occupied, right. So you will see the formation of Bose-Einstein condensates as temperature goes to 0, and then Maxwell-Boltzmann statistics has sort of a constant occupancy, right. So your beta term basically goes towards infinity as your temperature goes to 0, and for values of energy greater than Fermi level you just have a exponentially decaying occupancy of particles, right, with Maxwell-Boltzmann statistics. So this is a simple sort of exponential curve here. These two curves have slightly more complicated behavior, but you see that as you vary the temperature all of them should sort of converge onto the Maxwell-Boltzmann statistics, especially at high temperatures, right. So that is what we see in this curve here. At 0 Kelvin you have this step like behavior as you keep increasing temperature, and as you go to very large temperatures you see just a behavior of this Maxwell-Boltzmann type of statistics. Okay, so we saw that if you are dealing with quantum mechanical particles we need to sort of take into account different ways that these particles can actually occupy, so different occupancy rules. But for some classical systems we do not need to worry about these occupancy rules, such as an ideal gas, right. So an ideal gas we can actually treat this using simple Maxwell-Boltzmann statistics as long as the number of particles is far fewer than the number of possible states, right. This is usually the case when the density of the system is low, and it turns out that gases behave ideally when their densities are usually low, right. And gas particles can be indistinguishable, so we basically treat our partition function, and let us for simplicity take this treat this in a canonical ensemble. So we have temperature, volume and number of moles to be constant. So partition function is basically the partition function of individual particles raised to the power n, and since we have indistinguishable particles we avoid double counting by taking this n factorial term here. And the partition for individual atoms or individual particles we can sort of write this as a product of different contributions. Translation is fairly important, so gases move around, so how they actually move around that is fairly important here. Electronics, so whether their electrons are in their ground state or excited states, and also nuclear, right, so whether their nuclei are in their ground state and excited states. In general for ideal gases, especially at temperatures of experimental relevance, let us say 1000 Kelvin, 2000 Kelvin and so on, the nuclear and electronic energy states are usually far apart. So electronic energy states are of the order of electron volts far apart. So compared to the ground state, the excited state is a few EV away, and the nuclear excited states are million electron volts away usually. So we can safely assume that atoms are in the nuclear and electronic ground states. So if you take an ideal gas at room temperature or slightly elevated temperatures like 400 500 Kelvin, this should hold true, right. So for most practical purposes you can assume that this electronic and nuclear ground states are just electronic and nuclear partition functions are just one, where the atoms are occupying their electronic ground state and the nuclear ground state. So it is a singular well defined ground state, so the partition functions basically become one there. and translation basically we can model it as a particle in a 3D box, right. So as long as we model one particle very well, right, we can get the partition function for all the n particles, right, within our box. So we already defined the energy levels for particle in a 3D box in our in a couple of lectures back with our first discussion on statistical mechanics, where we had a small primer on quantum mechanics, right. So we can sort of write the energy levels as a function of 3 different integer values here, nx, ny and nz. So if you actually skip the math and calculate the sort of overall partition function that comes from the translation component, you can basically see that, you know, it will be 2 pi m kBt by h square the whole power 3 by 2 times your v, where v is your volume of your box, right. So nothing but a cube here, and the way we are getting this is basically doing this summation here. So we'll try to substitute epsilon L within this exponential term here, and we'll see that, you know, this exponential term is actually fairly a dense function. So instead of doing a sum, we can actually do an integral, and once we do the integral, we'll straightforwardly get this get this value here for our translation partition function, right. So the term in brackets here highlighted in green is actually related to the de Broglie wavelength of the atom itself. So this has some quantum mechanics interpretation also implied in it. So the overall partition function is basically this individual partition function to the power n divided by n factorial, right. And if you use Stirling's approximation, we can actually show that our Helmholtz energy has this functional form, right. So it's negative n kBt times ln of this factor here, 2 pi m kBt by h square whole power 3 by 2. M is basically the mass of your individual gas particles, and then times your v by n. So the entire term is in the logarithm here, minus n kBt. So there is an additional n kBt here, right. So I'll give a couple of exercises. So these are actually nice problems to try out. So you can actually show that using the Helmholtz energy that we have derived here, you can actually show that the pressure is nothing but n kBt by v, right. So n is the number of particles, kb is your Boltzmann constant, T is temperature and volume, and we see that, you know, this is actually very closely related to our ideal gas. So if you actually write n as n by Na, where n is the number of moles and Na is the Avogadro number. Sorry, if we write this as, apologies, if we write this as n as n times Na, number of moles, this is Avogadro number, we can now write our pressure as n times Na times Kb times T by V, and this Na times Kb is nothing but our gas constant. So we can write P as nRT by V, right. So once you derive the pressure, right, and deriving the pressure is fairly straightforward. You take the Helmholtz energy that we defined in the previous slide, and you just take the derivative with respect to volume. Once you do that, you will see that, you know, it drops down to a simple term like this, and this is nothing but the pressure as we know from macroscopic thermodynamics as defined for an ideal gas, right. You can also calculate the internal energy and your specific heat at constant volume as well. So Cv is nothing but, we take the pen here. So Cv is nothing but dE dt at constant V comma n. So once you know the internal energy as a function of temperature, which you will define, which you can calculate from this Helmholtz energy definition here, you can actually calculate your specific heat, and you will see that, you know, it actually corresponds to, both quantities correspond to that of a monoatomic ideal gas. So these are nice exercises that you can calculate, that you can do with, and you can also derive your chemical potential, and you will see that your chemical potential sort of splits into two terms. So one constant term that only depends on temperature, and one term that has a pressure dependence as well, and this is related to how fugacity sort of and partial pressures contribute to your chemical potential term. So we can see that using a simple sort of canonical ensemble having indistinguishable particles which only go through translation, right, which only have translation as a degree of freedom, we are able to use simple principles from quantum mechanics and simple summation techniques to derive all the equations that we know from macroscopic thermodynamics associated with an ideal gas, right. So, these relations that you define here should be the same as what you know from macroscopic thermodynamics for an ideal gas, and this exactly shows the utility of statistical mechanics. So, we used quantum mechanics, principles from quantum mechanics, where we treated particle in a 3D box, right, and we used our statistical mechanics, basically Maxwell-Boltzmann distribution. So, combining these two, we are able to make the relationship from quantum mechanics to macroscopic thermodynamics, right, and this shows the utility of statistical mechanics. We can also generalize this to the behavior of diatomic ideal gas as well. So, in diatomic ideal gas, you will have rotation and vibration as possible degrees of freedom. So, we need to define a partition function for rotation of individual molecules as well as vibration of individual molecules within our ideal gas. For rotation, we basically have to model them as rotors with some kind of moment of inertia, and for vibration we can use we can model them with a harmonic oscillator, and both of these are popular systems that are that have been dealt with in quantum mechanics. So, we can sort of use the mathematics that has already been derived in quantum mechanics for an harmonic oscillator and for a rotor, and we can incorporate that into a per particle basis and then generalize this into our overall system here. So, this should be the overall so there is a typo here. So, this is basically your overall partition function. Q translation times Q rotation times Q vibration is your individual particle partition function here. So, and if you actually do the math, right, and if you obtain results, so if you obtain how specific heat is actually varying as a function of temperature, it actually points to the genesis of our equipartition theorem, which is very popular in quantum mechanics as well as in thermodynamics. Equipartition theorem basically states that for every degree of freedom, right, you have a half kBT contribution to your overall internal energy of your system. So, the result is basically your genesis of your equipartition theorem, and if you actually plot your specific heat as a function of temperature, right, you will get a plot that sort of looks like this. So, at low temperatures only your translation is sort of activated, and as you increase your temperature, your rotation modes will become activated. So, your specific heat actually goes through a jump, and then at very high temperatures your vibrational modes will also get activated, and then your specific heat goes through another jump here. So, you see that your specific heat varies in value as a function of temperature, and this is one of the questions that we started out with in our first discussion of statistical mechanics, right. So, we said that statistical mechanics can help you understand why specific heat can actually vary with temperature in a given system, and we see one example of how and why specific heat actually varies in the case of a diatomic ideal gas, right. So, at low temperatures only the translation mode is active, right, and then you have a transient region where your rotational mode starts becoming active, and then your rotational mode is fully active here, and then your vibrational mode starts becoming active, and then your vibrational mode is also fully active here, right. So, you see a very nice dependence of specific heat as a function of temperature. Okay. We can also extend this exercise to an ideal solid solution. So, just like an ideal gas, an ideal solid solution is also a very popular system in material science and in macroscopic thermodynamics, and we can model this using either canonical or grand canonical ensemble, right. So, if you were to model this with a we can also model this with a canonical or a microcanonical ensemble. So, let us say we take the case of a microcanonical ensemble. We say that n out of n sites are occupied by one atom type, let us say A, and let us say the energy is basically a function of the number of atoms of type A you have in your system, right. So, we can model this energy as m times your epsilon. So, we can have a degeneracy, this is nothing but your number of combinations that you have, and your entropy is kB ln omega, right. So, for large values of n and m, right, we can basically use Stirling's approximation and derive entropy as negative n kb x ln x plus 1 minus x ln of 1 minus x, where your x is nothing but your where your x is nothing but your m by n. right. So, it is the total number of your atom type A, so or some kind of a mole fraction of your atom type A divided by the total number of sites that you have, right. So, that is your x here, and this relation is very well known, right. So, this is identical to macroscopic thermodynamics, and since we have an equivalence of ensembles under large sizes, right, we can use this entropy definition to be incorporated to our Helmholtz energy. So, Helmholtz energy is nothing but E minus Ts, right. So, this is basically your Ts term and this is your E term here, right. So, we can actually derive our Helmholtz energy, and once again I will give a nice take home exercise here. So, try to calculate what x or what mole fraction here minimizes your F by n term here, right. So, I am not normalized my n here, but if you actually take n, right, you should get F equals x times epsilon plus kBt epsilon x plus 1 minus x ln of 1 minus x. So, you can actually try to determine what x minimizes your F by n, especially for epsilon far greater than kBt, right. So, under these conditions you actually your models actually mimic the scenario of defect formation. So, you can actually consider your epsilon to be a proxy of your defect formation energy, right, in this scenario that your epsilon is far greater than kBt. So, you can try to evaluate whether the result is identical to what you will calculate as equilibrium defect concentration from macroscopic thermodynamics. If this is indeed true, then you have once again established a very useful equivalence or very useful utility of statistical mechanics in how that can be used in modeling a simple ideal ideal solid solution here. So, we have gone from a simple energy model here of how atoms of a type are contributing to the energy of a system and principles of microcanonical ensemble to entirely define macroscopic properties associated with this ideal solid solution. So, another example of the utility of statistical mechanics. So, with that we are coming to the end of our discussions on statistical mechanics. So, we have established statistical mechanics as a bridge across length scales. The sort of statistical mechanics includes or stands upon two main postulates, which is the of ergodicity and equal a priori probabilities for isolated systems. We saw examples of three different ensembles: microcanonical, canonical and grand canonical, and all three ensembles are equivalent under large system sizes, and we saw specific examples dealing with two state systems and how these can be the principles of microcanonical, canonical and grand canonical ensembles can be extended to ideal gas and ideal solid solution. We also saw briefly that if you want to if you have systems of indistinguishable particles, especially those that have certain occupancy rules, you may have to use different statistical functions such as Fermi-Dirac statistics or Bose-Einstein statistics to model them appropriately. So, with that we come to the end of our discussion on statistical mechanics. In our next lecture we look at lattice models and sampling techniques. So, I thank you all for joining today's lecture. I will see you all in the next one.